Hello again. My name is Radim, and I'll speak on behalf of mostly Czech team from the Czech Republic, who measures tree growth in SAFE. And the project is led by Martin Svátek, who's sitting over there. So if you have any questions about the data, ask him. So, and I'm going to present today some of the results that indicate that selective logging makes the tropical rainforest in Borneo more vulnerable to drought due to species composition. And we have heard a lot about it. Just the selective logging is different from here. It targets only commercially valuable timber species, removes basically the large high biomass trees. And obviously, it alters structure, kind of opens canopy and changes composition. It's not restricted to Southeast Asia. It's everywhere in my experience, but it's most intense in Southeast Asia due to high abundance of dipterocarps, which are the commercially valuable species. So they represent a high proportion of the biomass. So that's why it's very important, especially in Southeast Asia. So then, obviously, there are differences in composition, and in the old-growth forest, it's dominated by late successional species. In Borneo, mainly dipterocarps, we know. But when we remove the dipterocarps, obviously the forest is dominated by non-dipterocarps and often by pioneer species. In Borneo, the Macaranga genus is the most common. And in our research, we study forests. We are foresters, most of us. So we study how logging affects tree composition and along the logging gradient in SAFE. And we also focus when the logging stops, how the forest recovers, whether the degraded forest recovers quickly or not. And obviously, if we change the functional composition of the forest by target harvesting dipterocarps, then we also expect that it changes growth and productivity patterns, and also might affect forest resilience to drought. We are working in four blocks in the B, E, LFE, and VJR. We have heard about that. I'm not going to explain more, but we are restricted to 38 vegetation plots in the 4 blocks, and we measure basically all trees greater than 1 centimeter in dBH, but we do it yearly. So we remeasure all the trees. We've been remeasuring them since 2011. The logging gradient is represented by different qualities in our research. So we have these qualities from 2 to 5. 2 is the lowest quality, heavily degraded forest. Up to 5 is the old-growth forest. Here. So we are using this field map technology, which is laser-based technology that combines laser, fine ranger, compass, and laptop. That when it's together, you get very precise positions of each tree. So you have very nice, very good maps of the trees. Then we can come back year after year and remeasure the trees. We also add new trees. And because there is a Z coordinate registered automatically, so we can get also 3D models of the plot. So what we have observed so far, and then how the effects on composition, and lighter gray means greater degradation. So the quality 2 is here, and here we have dissimilarity to VJR, to the old-growth forest. So we see that the values of the index are around between 70 and 0.7 and 0.9. 1 is complete dissimilarity, 0 is complete similarity. Here we are over 0.7. So all the logged forests are very different from old-growth forest, and it's especially the quality 2 is very, very different. What's interesting, there are averages for years, and there are trends here over the time we've been studying that, and you see no development. There's some kind of slope, but it's not significant. So we would think that not much is going on with the composition, but it's not true. Because when we look at genus turnover, because we are testing it on the genus level, because we are sure with the genus, so it was quite high species turnover that increased over time, and it was calculated as a dissimilarity to the first year. So, and the turnover was highest in the most degraded plots, so there was change in species composition. So the conclusion from this are that selective logging changed the species composition, or genus composition in this case. And the dissimilarity increases with increasing logging intensity. So more you log the forest, the more different the composition is. It's kind of intuitive, but it's nice. So here, so what's interesting is that we observed no improvement of forest quality over time, and despite the high genus turnover. So that's what we find interesting. When we look at the main groups of species, the pioneers and dipterocarps, here again, the most degraded forest, quality 2, light gray here, and light gray here. So obviously the more degraded forest, the more relative abundance of pioneer species and lower abundance of dipterocarps. And here for quality 5, the black color, it's opposite. It was around 10% or less of pioneer species, and more than 40% of dipterocarps. So there's quite big difference. It's nothing new, but there is a scale depending on the intensity of logging. Yeah. So there is a very. Oh, I'm going back. There's very little shift when we look at the development over time. We see some kind of decrease in the relative abundance of pioneer species, but it's mostly not very significant. And there's some increase in dipterocarps, but it's 1, 2, 3% over time, but nothing really dramatic. So there is something going on, but not really much in terms of this relative abundance. So when we thought, okay, so there are more dipterocarps in old-growth forest and more pioneer species in integrated forest. So we compared these groups, and we classified trees as either dipterocarps, pioneer, and other species. So, and the red here there are dipterocarps, and we calculated relative basal area increment, yearly increment per plot. And I'll start with the green pioneer species. You see that there's kind of a greater relative, greater growth increase in. I'll go first to the years. We have here growth from 2014 to 2018. And here, 2016, it was all year El Niño. It was drought all year. But it started already in 2015. So these 2015 and 2016 are affected by El Niño. The others are not. So here in 2014, we have growth unaffected by drought, as well as we have the same here for 2018 after El Niño. So before, you see the pioneer species, they had greater growth, as we expect. They are typically a fast-growing species, but it declined massively during El Niño, and it did not recover. It stayed really not so. The recovery was really poor. In comparison with dipterocarps, we see that not much effect of drought on the growth of dipterocarps, but we see some kind of recovery here, very rapid recovery. The other species were kind of not much really, they were affected, and the recovery was not really big. So it was the basal area. When we look at the absolute values, absolute growth in terms of DBH increment of individual trees here, it's kind of very similar pattern. Here, again, before the El Niño, the pioneer species grew very fast, faster than other species. Then the growth dropped a lot and did not recover much. Instead, dipterocarps were also affected slightly. You see some kind of decrease in growth, but then recovered. Immediately the year after, they grew very fast. So when we calculated also the relative basal area, that died, yearly change in mortality per plot, and we saw that this is the I didn't mention that this is the average value for all species. So this is average mortality over all years for all species. So Dipterocarps were mostly below the average of the. Instead, Pyrenees were above that line, but we see that here was El Nino, then it stopped. But there was the year after the El Nino, there was a big increase in mortality of Pyrenees species. There was some increase in Dipterocarps, but it was not really a significant decrease. And then in other species, there was increase in mortality during the El Nino. But I see that there's a big difference in the patterns here between Dipterocarps and Pyrenees species. So for this we used yearly data to understand better what's going on, because even a moderate drought might affect trees. And so we installed. You can find these devices there on about 50 Dipterocarps and 50 Macarangas. These automated dendrometers that we built ourselves. They are resistant to the Berninian climate, so they work there. They've been there for a year now, and together with the soil probes. So we actually have the microclimate data and soil moisture data from the plots. So they record every 15 minutes temperature, soil moisture, and the stem diameter change. And what's good about that, we get very precise data what's going on with the tree. You leave it there, come in 1 year, and you see what happened all the time, every 15 minutes with the tree. There are daily changes in stem diameter as the tree transpirates. It uses the water from the stem, so it shrinks. And when it refills the water in the stem, it expands again. So there's daily dynamics. But when there's not enough water, the expansion following the shrinking is not enough. So the tree starts shrinking the diameter. So here, the red line is the line. It's an example of the data for Macarangas, and the black line is for 3 Dipterocarps. They started at the same value here, but after only 7 days, and during a mild decrease in soil humidity, you see that we registered a small growth in Dipterocarps, but shrinking in Macarangas. So it even further supports the previous results that Dipterocarps are much more resistant to drought than Macarangas. So the conclusions, first about the composition, that we see that the logging really changes the tree composition. It's not good. Whatever, we know that. But the impact, the negative impacts increase with increasing logging intensity. So it's very important to look at the intensity of logging, not only where it was logged or not. And despite great genus turnover, we haven't seen any signs of post-logging recovery towards better quality. So it's really slow development over there, I think. And so it also emphasizes the long-lasting consequences of selective logging for tree species composition in lowland forest, because sometimes people say, oh, it's only selective logging, it doesn't do much, you leave most of the trees there. It doesn't change much, but we see that it changes a lot. So, and in terms of the Pyrenees and Dipterocarps here, they were really only very weakly and temporarily affected by the El Nino drought, whereas the Pyrenees species grew initially faster than Dipterocarps, but then the growth fell down and did not recover. It's important that the El Nino stopped, the drought stopped, but the growth did not recover. And so the drought very much increased the mortality of Pyrenees species, but not mortality of Dipterocarps. So that's the conclusions are that Dipterocarps, they represent lots of biomass in Southeast Asia, all-growth forest or primary forest. So they are important for stability as well as productivity and carbon sequestration, especially during the droughts. Whereas the Pyrenees species, they really grow fast when in wet seasons, when there's enough water, but when there's drought, the drought affects them very negatively. and over a long time. It's not only short-time effect. So this all indicates when these species composition changes indicate that this selective logging make tropical rainforests more vulnerable to drought over a long time. Yeah. And that's the final one. And thank you for your attention.